do. First of all, as you probably all know, the Barnes Aquifer provides water to 4 communities through 11 municipal wells. It provides about 5 million gallons per day of water pumped. And of course, the Easthampton portion of the aquifer was designated by the Environmental Protection Agency as a sole source aquifer in 1995. This is a map of the aquifer, and the,
oh, you're fine.
You know what it is. This part of the aquifer is the crosshatch area represents the sole source part. It's designated at a time before the well of concern that we're going to talk about tonight, where the recharge area for that well was actually determined. So this is the area that supplies water to the primary municipal wells in Easthampton, which are all located here. There's one in Nonotuck Park, then there's the Hendrick Street well field, Pines well, and Brook Street well. These are all supplied in this general area. They're recharged in this general area through here. But the Barnes Aquifer extends to other areas as well. Area of Southampton here, Southampton has a well, and Westfield actually has a number of wells that they use to get water. So, why is the Barnes Aquifer Protection Advisory Committee concerned about the landfill? And I'd like to go through some of the criteria that the DEP has for citing landfills and to show that they have basically ignored their own criteria. And basically their criteria says that no site shall be determined to be suitable where it lies within a zone 2 of an existing public supply well. And of course, the Maloney well, which was the northernmost well in that sequence of wells, does lie within, the landfill does lie within the zone 2 of the Maloney well. And either go further and say that any area of recharge, any area over recharge area of sole source aquifer, and of course technically it's not, the landfill's not in the sole source aquifer area, because at the time that the sole source aquifer was determined, where the Maloney well was being recharged was unclear. And in fact, I did not think it personally. I thought it didn't come from the area where the landfill was at all, and I was proven wrong by the DEP later on. And of course, there shouldn't be any existing or potential public or private water supplies down gradient. And of course, that's not true either. There's lots of potential aquifer in the area downstream from the landfill. And it's really a question of, even if we're not using this aquifer today, everywhere we go, we know water is becoming more and more scarce a commodity. Can we afford to give up some of our supply? And I think the answer has to be no. Okay, so now what I want to do is talk about why we think that the Northampton landfill is located in really a critical part of the primary recharge area for the Maloney well. This is a sort of a map that shows the aquifer here, and then we've drawn some flow lines on here to show how water moves through the aquifer. And I want to say that when I first started working, I've done a lot of work in the aquifer, and I always believed that this bedrock ridge actually extended across here, so water from this side didn't come across to the other side. And when the DEP first started considering the landfill, that's what I told them, I don't think it goes across there. I don't think we're in the zone 2 at all. The landfill was in the zone 2 at all. And the work the DEP did was to show that indeed there is a connection between the two sides. So now we know there is a connection between the two sides, and the flow paths seem to look something like this. And you can think of the Maloney well sort of being at the intersection from water that's moving to the north from the what I'll call the eastern side of the aquifer, and water moving from the north from the Southampton area, and then water moving eastward from where the landfill is. Now, it's not just the Northampton landfill, and this might be bad news to us in Easthampton to realize that there are 2 other landfills, the Oliver Street landfill and Loudville Road landfill, both have been closed, but these also are potential sources of contamination to the Maloney well. And in the long term, the three sites together are, I think, what produce a problem for us. So this is a geologic map, and it's what we call a superficial geologic map, and it's a map of the surface sediments. And here's the Maloney well here, and the blue areas represent clay deposits that are exposed on the surface, and this, it doesn't show up very well here, but this sort of lighter colored area here represents some sand, but this is on top of the clay. And then we get over to the far edge of the aquifer, and we see some red material here. This is where sand and gravel is exposed out on the surface. These are the areas that are the primary recharge area for the aquifer that extends out here. Now there's also a primary recharge area down on this side as well that's moving water up this way. So that's why I said the two come together here. So what I want to do is to show you why this is so. And I guess I should start out by, I like to show this slide to show you, well, what does the aquifer really look like? If you could go down in it and look and see what it is, what does it look like? Well, it looks something like this. It's layered or stratified sands and gravels, well sorted on the whole, some very gravelly layers, some sand layers that are very permeable, and so water can move through. But there's not large open spaces, it's moving through this kind of material. So how did this material get here? And you know, one of the nice things about being a geologist is that when you study these things, you have to go out and find modern analogs for how the deposits were formed in Easthampton. Well, we need to go to some place that can take us back to see how those were actually formed. So we go to Alaska, and here's a glacier in Alaska. And of course, anytime you go near a glacier, especially today, there's a lot of meltwater coming off the glacier, and it's transporting sands and gravels and depositing these sand and gravels out in front of the ice. And here's another one, the ice in the background. There's actually some people here for scale, and you can see how coarse this gravel is that's being deposited up front from the ice. And this is all sediments that are being deposited quite rapidly, thick deposits of sands and gravels by these meltwater streams. This is what the material that's going to make the best aquifer. Now the other thing, if you go to modern glaciers today, you'll find there are a lot of lakes. And here's a glacier terminated in a lake. And of course we know in the Connecticut River Valley here there was a glacial lake. And that lake, Lake Hitchcock, covered, actually extended from about Middletown in Connecticut north all the way to St. Johnsbury in Vermont. And this is where it was here in the local area. This is a digital elevation model. It's kind of an odd view perspective. We're looking to the southeast. Here's Mount Tom, the Holyoke Range. You might be able to pick out where the Connecticut River flows through here, and the Oxbow back in here. And even you can see the fill from Interstate 91 there. And of course, Easthampton, we're located over in here. And we see these high areas shown in yellow, and this would be one of the recharge areas, the primary recharge areas for the wells like the Northampton Park well and the Hendrick Street wells. And then the Maloney well, which is located about out in here. It's right out here in the middle of the lake. So we need to understand how these sediments have accumulated and how they all put together to form the aquifer. Well, the lake sediments, the glacial lake sediments, are really interesting in themselves. They're fine grained. They're clays alternating with silty sands, and they're called varves with a V. And they're kind of neat because each sand, silt, and clay layer, these two layers combined, represent 1 year of deposition in the lake. And you can count back and see how many years the lake was here. But you can see that this material is not very permeable, certainly not very permeable vertically, although there might be some horizontal permeability. So that contrasts strongly with those coarse sands and gravels. So that material is not going to be permeable. The sands and gravels are going to be really permeable. And then the other thing is, if you go out on one of these lakes, and here we are on a lake right in front of the ice here, and you drop a current meter down into the water, what you will find is you can find where the meltwater streams are coming out from underneath the ice. They're coming out in tunnels underneath the ice, and they're streaming out, and they're causing deposition of coarse sands and gravels, those same sands and gravels, but underneath lake level, right at the bottom. And of course, every year the ice front melts back a little bit further. And so as the ice front retreats back, underneath the lake, there's a layer of sand and gravel being deposited. We could sort of view it something like this. Here's our ice front. In this case, the ice front is standing in one place for a long period of time. It's building up a thick pile of these outwashed sands and gravels like we saw in Alaska. Now we're going to start melting the ice front back. And as we melt it back, we form a lake. And the lake, in the bottom of the lake, we get the bar of clays. And then as we get close to the ice front, we see more sands and gravels being deposited. And these sands and gravels will vary in thickness depending on how long the ice front sits there and how much meltwater comes in. But of course, as the ice front continues to melt back, then these sands and gravels will be covered over by the bar of clay. But where these sands and gravels were built up above lake level at the ice front, sort of the margin, where it stood for a longer period of time, then they're above lake level and they don't accumulate any sands and gravels. So, in the end, if we take this picture and look at it this way, we see that we have our sands and gravels here that extend underneath the clay. And that's the critical point. And that some areas we have the sands and gravels exposed on the surface. And these are the recharge areas where water that falls to the ground can enter into the aquifer system. And then other areas, the clay is covered over the surface. And so it's hard to get water down through it. And even some places where the potentiometric surface or the pressure surface is above ground level. So in fact, if you were to drill a well here, and you drill into the aquifer, the water would actually spray out onto the surface. And of course, in those areas, there's just no way to recharge the aquifer here because the water's coming up, it's not going down. It's coming up. And so if we go to the Maloney well and look at one of the observation wells near the Maloney well, this is one of the observation wells that were put in when the Maloney well was installed. We see there's a hole drilled in the cap, and you can see the water spraying out. It's spraying out, it always sprays out. Okay, because here we have clay confining the aquifer. So there's no recharge around the well here. The well doesn't get recharged here at all. It has to get recharged from some distance away. And where does it get? So here again, it's a Maloney well with the fine-grained stuff. Where does this get recharged? Well, a little bit from here and from here. This is the recharge area. And of course, this is where the landfills are located. Okay, so our concerns. Some specific concerns. The impact of the current landfill on the Barnes Aquifer has not been adequately addressed. And, you know, we've looked at some of the reports, and some of the reports are of rather poor quality, and they don't tell the full story of what's happening. So if you're going to make decisions based on those reports, you might make the wrong decision. And let me give you an example. Okay, so this is this is the Northampton landfill as it currently exists. This right here is the Oliver Street landfill. It's pretty close. These two things are close together. These are wells that have some unusual chemistry. This well is contaminated with arsenic. This has got some other stuff in it. So I'm going to talk about that a little bit in a moment. And what we're going to look at is, and you might, if you're close, you might see this. But in this area right here, there are a whole series of seeps where groundwater that's moving through the landfill is coming to the surface in this wetland area. And as it comes to the surface, it precipitates iron and manganese. This is a very red sediment. It's a flock, what we call flocculent sediment, where iron and manganese are being directly precipitated as the groundwater comes to the surface. So the groundwater has tremendous amounts of iron and manganese that have been mobilized from the aquifer and are being precipitated in this area. So there's a well in there. There's a well in this area, and the results of looking at the chemistry from this well are kind of interesting. They show that from about 1998 to 2000, 2008, December 2007 or November 2007, I think was the last sample, we see a statistically significant increase in the iron concentrations from down around 10 or a little less than 10 milligrams per liter up to above 25 milligrams per liter over that approximately 10-year period. Concentrations are increasing. These concentrations are the result of leachate moving into the aquifer and mobilizing iron and manganese, again, a statistically significant increase. Now the problem is, if you read the latest Stantec report in December 2007, they failed to note this trend. In fact, they said the concentrations were going down. So, you know, if you were to read that, you would think there was no problem at all. But this data, which was obtained from their report, which they never bothered to plot, shows a different story. And so, you know, you have to be a little concerned when you see concentrations increasing, and you have to ask, why is that? Now, in fact, in fairness to Stantec, that if you go back in time, so this is the same data, but going back through some of their earlier reports from an earlier time, we see that concentrations did drop here initially. And why did they drop? Well, they dropped because the unlined part of the landfill was capped in 1995. And so the assumption is you cap the landfill, and of course that's going to reduce or eliminate the leachate generation. And it did. It dramatically reduced it. But it's now continuously increasing. And we need to know why it's increasing. It's certainly telling us that more contamination is getting into the aquifer. Okay, other concerns in that same area, you know, there are a whole suite of chemical contaminants that are in there. The one I think that is concerning to me is dioxane. The thing about dioxane, it was found in this one well, very close to the landfill, at 15 times the maximum contaminant level. Dioxane is a chemical that moves very freely, even through clay. So if you line your landfill with clay, dioxane goes through it pretty easily. So it's hard to contain, and so that's a problem. I do want to talk about arsenic, because I think this is one area that hasn't been fully addressed in any of the reports, and it is an area that I think needs to be of some concern, especially with regard to the Maloney well. Arsenic mobilization is expected in landfill leachate. This is something that is well documented in the scientific literature. And despite the fact that one of these domestic wells downstream has been contaminated, has high concentrations of arsenic, this issue has really not been fully addressed. Now, let's be perfectly clear about arsenic. There's a lot of natural contamination by arsenic in New England. And this is just a map. You don't want to be having to get water from this area in Maine, because there's a high probability of arsenic contamination naturally occurring in the bedrock. We get out here to western Massachusetts, and it's not too bad, except for the local area, the Connecticut Valley. The red rocks that we see in the local area are susceptible to arsenic contamination, naturally arsenic contamination. So why do I think that this could be related to the landfill? And I just give you a title of a recent paper in Applied Geochemistry. It's talking about naturally occurring arsenic mobilization at a landfill in Maine, implications for remediation. What this paper basically says is that the leachate from the landfill mobilizes arsenic that's naturally occurring in the rock. So the arsenic's not coming from the landfill at all. The arsenic is present in the area. And what happens is the leachate changes the chemical composition of the water by reducing dissolved oxygen and mobilizes arsenic. Here's the flock. We said the flock was iron and manganese. Well, the arsenic is commonly associated with the flock. And another paper, arsenic-rich iron flock deposits and seeps down gradient of solid waste landfills. This is a well-known, well-documented story where if you look at these flocks, and this was a study done in New York State, that they found whenever they looked at these flocks just like this, they found very high arsenic concentrations. Because again, the leachate from the landfill is mobilizing arsenic. Okay, so why did I go through all this in terms of the Maloney well? Our concern is that we have 3 landfills here, and the landfills are all producing leachate, and that leachate is using up dissolved oxygen in the water. And that dissolved oxygen, the lack of that dissolved oxygen, will cause things like arsenic to become mobilized. The Maloney well, located right here, already has a high manganese problem. That high manganese is associated with relatively low dissolved oxygen. It already has fairly low dissolved oxygen. I like to use the analogy of a lake. If you're putting nutrients into a lake and you get eutrophication. And so if you put more nutrients in, if a lake is almost eutrophic, you don't want to put more nutrients in because it will go eutrophic. You think of the Maloney well as sort of being on the brink. And this is a little groundwater model that we've been playing around with. It's not the answer at all, but it's just a simulation that we've been doing. And what we're doing is we're simulating the natural dissolved oxygen in the system, and we're successfully showing that the Maloney well has low dissolved oxygen. We can do this simulation without putting the landfills in there. When you add the landfills, what happens is you see how these 3 landfills influence this large area here and come in and potentially could influence the Maloney well and make that well have increased arsenic concentration. The arsenic's not going to come from the landfill. It's going to be the change in chemistry because you're loading the aquifer with leachate, and because we have this extensive area of clay deposits, you can't get dissolved oxygen down through the clay. It's got to only come from the recharge areas. So our conclusions is the landfill expansion violates DEP and aquifer protection rules, and these are conservative rules, and we think that we should view our water resources in a conservative way. And so we shouldn't put a landfill someplace where there's a potential for contamination. The landfill, in fact, lies in a critical recharge zone, principal recharge zone of this aquifer. And I think that we could say that the current studies of the landfill impact are really inadequate. And I think if you look at some of those reports, you would see that they're not adequately addressing these issues. And I think we would also conclude that there is evidence from those increasing concentrations that the contamination from the landfill is in fact increasing. And so if this were to continue over a long period of time, then we would see the impact on the Maloney well. Now, one of the problems that we have in dealing with this issue is that anything that's done in the landfills, the impact on, say, the Maloney well is going to occur 25 to 50 years in the future. It's not going to be something we're going to see rapidly. It takes a long time for these impacts to occur. So the idea is that if you're going to, you need to protect this thing for the future. And when water demands are going to increase, we don't want to be seeing our water quality decrease at that time. So that's basically the story, and I'd be happy to answer any questions.